Hey everyone. So in this video I'd like to say a few more things about sine and cosine. So in the previous video we defined these two trigonometric functions. We said that if we have a circle of radius r and we look at an angle of theta along the center of that circle, well, at the end of that angle and on that circle there's an associated point with an x-coordinate and a y-coordinate. And so we defined cosine of that angle theta to be the ratio x divided by r, right? So this measurement here divided by the radius of the circle. And then sine of theta, well, it's the ratio y divided by r, so this measurement here divided by the radius of our circle. And we made the point that these ratios, they don't change if we look at a circle of different radius. They really just depend on the angle, and so we can just look at the unit circle, a circle of radius 1. Right? So if I have a circle of radius 1 here, and I look at an angle of theta, right? Cosine of theta and sine of theta are really defined the same way. But because we're looking at a circle of radius 1, well, we have x over 1 as the ratio, right? X over r, x over 1 in this case. So we just have x. And on the unit circle, well, sine of theta is that ratio y divided by r, where r is 1 in this case, so sine of theta is just y. And really the takeaway from this is that on the unit circle, well, the x-coordinate is the same thing as cosine of theta. And the y-coordinate, well, that's just the same thing as sine of theta. So the points on the unit circle really describe cosine of theta and sine of theta. Okay, so let's go ahead and warm up with these two examples here. I want to determine sine of negative 4 pi over 3 and cosine of 17 pi over 6. If you're feeling up for it, please go ahead and pause the video and try these examples yourself, and then we can work on them together. So with this first example, what we really want to make sense of before we really begin is this angle, negative 4 pi over 3. So there's sort of two things you want to think of. One is the fact that it's a negative angle. We're talking about clockwise rotation. And then, this angle is being described in multiples of pi over 3. And pi over 3 represents a 60-degree angle. So this is like saying negative 4 sets of pi over 3. So you can kind of think of this angle here as, well, here's one set of pi over 3, one set of 60 degrees. In the clockwise rotation, this is a second set of 60 degrees. This is a negative 2 pi over 3. This third set would bring us to negative pi. And then a fourth set, the final set, would be negative 4 pi over 3, the angle we're trying to consider here. And so at the end of the day, this entire rotation, that's that negative 4 pi over 3. And if we can imagine fitting a triangle into this picture, right, so this angle here, in the triangle, that's pi over 3, that's 60 degrees, right? That last chunk that we added on to negative pi, that was a pi over 3 measurement tacked on to the end to bring us to that negative 4 pi over 3. And so that's 60 degrees. This here is 30 degrees. This would be like pi over 6. So this is a 30, 60, 90 triangle. If we're talking about the unit circle here, then this measurement at the bottom is negative 1/2. If we're considering the fact that we're looking at our coordinate plane here and we're on the left side of the y-axis, this measurement is positive square root of 3 over 2. And so sine is the y-coordinate of a point on the unit circle. So it's this measurement here, it's the square root of 3 over 2. Right, so maybe I'll just write it down here. Sine of negative 4 pi over 3. That's equal to the square root of 3 over 2. Okay, what about this next example, cosine of 17 pi over 6? Well, 17 pi over 6, we can kind of break it up. We can kind of see it as 12 pi over 6 with an extra 5 pi over 6 on top of that. And so 12 pi over 6, this is the same as 2 pi, that's a full rotation. And then we still have 5 sets of pi over 6 to add on to that. And so pi over 6, right, that's 30 degrees. And so if I add one set of 30 degrees, I'm there. Another set of 30 degrees, a third set, a fourth set. Maybe that one's not so good. A fourth set, and then a fifth set. Right, so here, this is the angle measure we're looking at, or the terminal side of our angle. And so, there's a triangle we can kind of fit in here. This triangle here, where this angle is 60 degrees, this angle is 30 degrees, and this angle is 90. And so if this is the unit circle, then we have a side length of 1/2 here. We're talking about a negative x value because we're on the left side of the y-axis. This is a negative square root of 3 over 2, right? The larger leg opposite the 60-degree angle. And then cosine, right? This is the x-coordinate on the unit circle of the terminal point. And so here we have cosine of 17 pi over 6. Well, this is equal to negative square root of 3 over 2. So those were two examples of computing outputs of sine and cosine, and really we've only computed outputs of sine and cosine that came from input multiples of pi over 3, pi over 4, and pi over 6. And I just want to take a moment to emphasize that really we can input any angle into these two trigonometric functions. We'll typically stay with these nice angles that are multiples of pi over 3, pi over 4, and pi over 6, but really we can plug in any angle into these two functions. Though typically, outside of our special angles, this will require using a calculator. And just like we could compute sine or cosine in degrees or radians, a calculator can do the same. And so when you're trying to compute the value of sine or cosine using a calculator, you need to be aware of what mode your calculator is in. So usually, I think the default for a calculator is that it's using radians, it's in radians mode, but oftentimes you can find in your settings for your scientific calculator which one it's using, and you can also make the switch. And just to emphasize the importance of this, let me just say that we know what cosine of pi is. And if we're talking about pi radians when we don't include a unit, right? So pi radians corresponds to this angle halfway around that circle, right? So here we end up with this terminal side, this point. If we're talking about the unit circle, this is the point -1, 0, and cosine of pi gives us that x-coordinate on the unit circle. So we get -1 out. Now, if your calculator thinks degrees, you're talking about degrees, and you say pi degrees, well, pi is the number 3.141592, so on and so on. And so cosine of pi degrees is saying cosine of roughly, a little bit more than 3 degrees. You'd be talking about, roughly this angle here. And if you try to find the cosine of value of this point, well, I can't tell you exactly what it's going to be, but it's going to be some number, or I guess I did compute this ahead of time. It's roughly 0.9984, right? So some number close to positive 1 because that's a really, really small angle there. So we get pretty different outputs because the calculator interprets these two very differently. So another way we can compute the values of sine and cosine is by recognizing that they describe points on the unit circle. And points on the unit circle must satisfy this relationship x squared plus y squared is equal to 1, right? The equation of the unit circle. And usually this isn't enough to completely decide sine or cosine. You'll usually need a little bit of extra information, but this is one way you can kind of get one trigonometric function value from the other. And so let's see an example of this. So here this problem says, if theta is an angle in quadrant 3, and cosine of theta is equal to negative 3 over 5, determine sine of theta. So recall that we can break up our coordinate plane to quadrants, and usually they're labeled in counterclockwise order, right? Quadrant 1 in the top right, quadrant 2 in the top left, 3 in the bottom left, and 4 in the bottom right. So we're saying that this angle theta, it's associated, it falls in this quadrant 3. Now, if we're thinking about cosine of theta, we can think about dealing with the unit circle here. And we're saying that cosine of theta, the x-coordinate of the point on the unit circle here, is negative 3 over 5. So negative 3 over 5 is, as an x value, it's roughly here, right? So maybe we'll just draw the line here. This is the line x is equal to negative 3 over 5. So there are 2 points on the unit circle here that have such an x value. But again, we're talking about the point on the unit circle in quadrant 3. So we're really talking about this point down here. So here, we don't know the angle. We actually don't even need to worry about the angle. We can compute sine of theta by recognizing that, well, if the equation of this circle is x squared plus y squared is equal to 1, and we know that the x coordinate of this point is negative 3 over 5, right? We can determine the y coordinate of the point from this equation. Right, so I square negative 3 over 5, I get positive 9 over 25. Then I subtract away 9 over 25 from both sides. And then here you can kind of think of 1 as 25 over 25. Right, 25 divided by 25 is 1. Anything divided by itself is 1. Subtracting 9/25 from both sides gives me that, this should be y squared. Y squared is equal to 16 over 25. And then the two values of y that make this true are positive, right? I take plus or minus the square root of both sides to get y needs to be plus or minus. We can break apart square roots across division, and I would take the square root of the top to get 4, and the square root of the bottom to get 5. Plus or minus 4/5. Well, in this picture, what's the y value of this point? We know it's negative, right? It's below the x-axis. So we're really dealing with negative 4/5 here. Right, so this point is the point negative 3 over 5, comma, negative 4 over 5. And so that tells us that sine of theta, right, the y coordinate of this point is negative 4 over 5. We actually didn't even need to know the angle here. We just needed to know its x coordinate. And we needed to know what quadrant that angle was in. That was enough information to figure out sine of that same angle. So in the previous problem, we used the idea that the equation of a unit circle is x squared plus y squared is equal to 1. And that sine of theta and cosine of theta described the points on the unit circle. Another way that we usually see those ideas put together in trigonometry is that sine squared of theta plus cosine squared of theta is equal to 1. And before I really justify this statement, so this statement is true for any value of theta, I want to make it clear what this statement is really saying. Okay, so there's a little bit of new notation here. And so, if I had something like sine of theta squared, if I just wrote this out, there's a little bit of possibility for confusion here. Right? Does this mean take my angle theta and square it and then compute sine of that new squared angle? Or does it mean sine of theta, compute that first and then square the result, right? So there's ambiguity as to what this could possibly mean. And just to avoid this altogether, the convention we have for writing exponentiation of trigonometric functions is to write that exponent right after the function name before the angle, right? So sine squared of theta, this is representing the idea of sine of theta, compute that first and then square your result. So the above statement, sine squared of theta plus cosine squared of theta is equal to 1. That's like saying sine of theta, compute that and square it, cosine of theta, compute that and square it, add those together, that must equal 1. Okay, so this statement, sine squared of theta plus cosine squared of theta is equal to 1, this is called the Pythagorean identity. It's known as the Pythagorean identity. And an identity is an equation that's true no matter what we input into the values of the equation and into the variable of the equation. So no matter what angle I plug into this equation, it's always going to be true. The left side's always going to come out to 1. And so why is this the case? Well, if I have a unit circle here, and I look at an angle of theta, let me be consistent with colors here. Right, so here's the angle theta. We're saying that this point on the unit circle, its x-coordinate is cosine of theta, right? That's this distance here with a sine. Its y-coordinate is sine of theta. That's this distance here, this measurement here, also with a sine, right? Plus or minus. And so the Pythagorean theorem tells us that this side length squared plus this side length squared is equal to 1, is equal to the square of its hypotenuse, 1. And that's exactly our identity here, right? So the square of the y-coordinate, the square of this side length, plus the square of this side length is equal to the square of the hypotenuse, 1. So that's why we call it the Pythagorean identity. So we're going to talk about many more identities later on in this class, but I'd like to bring up 2 now. And so to motivate these 2 identities, let me ask the question, what are 2 angles, 2 non-coterminal angles? That produce the same output for the sine function? Can you think of any? Let me ask you to pause the video and see if you can. So one example of a pair of angles that give you the same value for the sine function is the angle pi over 6 and 5 pi over 6. Right, because sine gives us the y value of these coordinate or these points on the unit circle, and they both have a y value or a height of 1/2. Right, and really what's going on here is that we're sort of looking at the same short side of the 30, 60, 90 triangle. These are 2 ways you can kind of fit them into this picture above the x-axis. Right, so we get the same y value of 1/2 for both of these angles. And really the picture you should kind of have in mind here in generality is if I have some angle theta, Right, this point is going to have some y value. Well, what's going to be the angle that has the same y value, that corresponds to the same y value? It's going to look like a point corresponding to this angle here. Right? And what should this angle be? Well, I know the remaining angle to pi ought to be that same angle theta, right? So really, this angle here, the second angle, should be pi minus theta. Right? If we're expecting the same triangle to fit into this picture, both with that angle of theta to the x-axis, then for the second angle, we should expect 180 take away that angle of that triangle in red. And so that's pi minus theta. So sine of theta, this is going to always give us the same result as sine of 180 degrees minus our angle, or in other words, pi minus our angle. Right, just like above, we see that sine of pi over 6 is the same as sine of pi minus pi over 6, right? Pi minus pi over 6 is 5 pi over 6. So it's the same as our example here. What about for cosine? So for cosine, we obtain the same output when we input angles that are negative of one another. Right, so maybe for concreteness, if I have the angle pi over 4, right, this point, we're talking about cosine here, it has an x-coordinate. Again, if we're thinking of the unit circle, it has an x-coordinate of the square root of 2 over 2. Now if I think of negative pi over 4, well, cosine of this angle is this distance here. And again, we get the square root of 2 over 2. And really, if I go around theta degrees, not theta degrees, well, I mean, it could be degrees, theta radians, and I end up at this point here on the unit circle, right, then cosine of theta is describing this measurement here. Right, this is cosine of theta. And then negative theta would give me this angle with the same value, right? Cosine of negative theta gives me that same leg length with the sign attached to it, right? Plus or minus. But it gives me that same value whether I plug in a positive angle or a negative angle there. And so really what we're saying here is that cosine of theta, this is the same as cosine of negative theta. And we can kind of see it in our example above, just to have one concrete example, that cosine of pi over 4, this is the same as cosine of negative pi over 4.